about related topics which concern sparser or very sparse graph sequences, because part of the motivation behind studying these dense graph sequences apply just as well to these sparser cases, and also give a couple of examples and segues well into the main talk that you'll hear later on. So, what are the motivations behind all these graph sequence and graph limit theories that we are looking at? The objects of our study are graphs, meaning we take nodes and vertices connected by edges. Oh. Just a moment. Okay, is this, hopefully everyone can hear me now. Okay, so we look at graphs, which are objects, nodes, vertices that are connected by edges. From real life motivation, these describe networks, say the internet or the network of social interactions between people. And we'll denote by VG the set of vertices and by EG the set of edges. Okay, sorry. And the question we would like to ask is, if we are looking at very large graphs, then when can we say that these two are similar? How can we even tell that they are similar by looking at them? Obviously, if these are extremely large graphs, then we cannot just sit down and try to find an isomorphism between them or try to compare them exactly one-to-one. That's just too much information available that we cannot sift through. And so a similar notion that is connected to two large graphs being similar from real-world standpoint, networks or graphs in real life may be evolving with time. So you have a sequence of networks or graphs taken a snapshot of something at different timestamps. And you may ask the question, does this dynamic converge? Do you have some sort of a limit in whatever sense? So a possible answer to this question of what similarity means and what convergence then will entail, because if you have a notion of similarity, that may help you define a notion of distance between objects to measure how close or far away they are. And if you have a metric that gives you a natural notion of convergence. So let's try to define similarity. And a statistical physics approach to this would be, well, if you have huge objects that you cannot completely grasp, then let's take samples and have some empirical distribution of what we observe. And if these samples in whatever sense are close or similar, then we would like to conclude that the original big objects themselves are similar as well. So similarity is going to be measured through samples. Now, obviously, what does sampling even entail in this case? So what exactly is sampling? Well, one possible approach is to say, let's select a few vertices at random and see what this substructure of that big network or big graph yields. So what do these vertices picked at random actually span? Now, okay, we use the word random, but that's not a uniquely defined notion. So what exactly do we mean by taking random vertices in this big object? And this is where the theory for dense graphs and sparse graphs is going to diverge very strongly, because these have to be treated in completely different, incompatible ways. And I'll explain why what works for one will absolutely not work for the other. Okay, so one possibility is to say, okay, I take k vertices, all of them identically, uniformly from the vertex set VG. So I take one vertex uniformly at random, then the next one independently from the previous one, again, uniformly at random, etc. I repeat this k times, then I obtain a sample of k vertices and look at what I have spanned there. Another option would be to say, okay, I pick my first vertex uniformly at random, but then my subsequent choices of the vertices I'm looking at is going to depend on the previous choices. Or as it's going to turn out, everything is going to depend on my first choice. Now, in both cases, you see that we are looking at a uniform choice for at least the first vertex. And that is because typically when we are looking at the large graph, even though it may come labeled, it's also a question about isomorphism of graphs. If we relabel the vertices of a big graph or a big network, we would still like to call it the same. So if we want to see that two relabeled versions of the same large graph are the same, then we cannot do anything else but sample uniformly. Otherwise, there would be some bias that differentiates a non-homogeneous network from a relabeled version of it. So we'll be looking into these two possible approaches to selecting at random. The first one, so IID uniformly distributed, is what I would call delocalized samples. And so as I said, you fix k and you choose k vertices uniformly at random from the vertex set VG, and then you look at what these vertices span. This yields an empirical distribution on the set of simple graphs on k vertices. And that's a finite set on which you have some distribution. And you can then say that the sequence of graphs will converge in this, okay, I wrote converge 2 times. So the sequence is said to be sampling convergent in this sampling sense if for every single integer k, the true distributions on the set of k vertex graphs converges. Okay, so for every single k, I look at this thing. And you may say that from a statistical physics point, again, or from a practical point, requiring such a thing to be valid for every single k is unrealistic. I will not be able to test this for all possible k. However, if you want to have a sound mathematical definition, you should not impose a bound on how big a sample you can actually take. Okay, so you shouldn't limit a priori your possible experiments, talking from a physics standpoint. So from a mathematical definition point of view, you cannot put an upper bound on the size of the sample. And so you say for any size sample, you should obtain something that converges. Okay, and also note that for every single k, the set of graphs on which these distributions live, this set is finite. Okay, so you have distributions over a finite set. This is very important because it will lead to some compactness properties later on that we'll be talking about. So in this notion of convergence, where you look at samples that are uniformly random and independent choices of vertices, what you have to note, if along the sequence, there's a square missing there, so that should be little of the number of vertices squared. So if along your sequence, the number of vertices in your graph Gn is little o of the square of the number of vertices, then this will actually all just tend to 0. It simply means that there are not enough edges in your graph to see anything structurally different from the 0 in the limit. Okay, so that's, again, when you talk about dense or sparse graph sequences, it's really dense or sparse sequences that you're talking about, because you have to talk about the density of edges along the sequence. So it's not one single number, but some asymptotic behavior of your sequence. So this type of sampling doesn't work if, say, your graph sequence is the sequence of cycles of length n, because then you have n edges, and if you take a random sample of k vertices, you will typically see an empty graph, and that doesn't carry too much information. So this, as I said, is going to lead to the limit theory for dense graph sequences, and as limit objects, so-called graphons, which were introduced by Lovász and Szegedy in 2006. So this is what I call delocalized samples and leads to the dense case. We'll come back to this shortly. Now, the localized samples, so the other approach where you take the first vertex uniformly at random and then you do dependent choices after that, is going to be more tailored towards the sparse case, for instance, cycles, where instead of taking the second vertex completely at random and then with high probability it will not be connected to the first vertex, you will start exploring from the first vertex you sampled. So you fix some radius r, you sample one vertex uniformly from your vertex set, and then you explore the neighborhood of that simple vertex up to your fixed depth r. Okay, so that's why I call this localized sample, because it starts from this first vertex and explores the graph locally. And this time, your empirical distribution is going to be on a slightly different type of object. It's not going to be simple graphs, but it's going to be special simple graphs which have one distinguished vertex, which we will be calling the root. It is the first vertex we sample. Right? That's sort of the center of this R radius ball. And so we'll have some empirical distribution on these types of objects. So we say that the sequence of graphs is locally or Benjamin-Ishram convergent if for every radius R, these distributions converge. Now, I've not formulated exactly what set this distribution lives on for a fixed R. And there's a reason for that. So if along my sequence, I do not have a degree bound on my graphs, then these neighborhoods may blow up. Okay, so if in my nth graph, all my degrees are equal to n, then just taking r steps, I will see larger and larger subsets of graphs. So it's not really a well-defined finite set as in the previous case. However, this can be helped if either you assume that there is a maximum degree along the complete sequence. So for every n, the degrees in Gn are bounded by a universal constant, or as has been shown by Lyons in 2005, this can be helped if you assume bounded average degree along the sequence and some tightness condition. So this tightness condition essentially tells you that, yes, you're allowed to have very large degrees, but not too many, and somehow in these distributions, the tail is decaying quick enough for you to essentially being able to ignore large degrees in your graph, okay, very roughly speaking. And in this case, the limit is going to be what's called involution invariant distributions. I'm not going into the full details of what exactly this means. The example I'm going to explain is if you have these cycles of length n, then the limit object, if you wish, can be formulated as you have the root and a doubly infinite path, and with probability 1, this is what you see. Okay, so this is a distribution on some objects, and I say that with probability 1, you will see a root with a doubly infinite path. This is an example we'll be coming back to when we look at this other version of localized colored samples. So what is this about? Well, we do the same as previously, except that we now actually allow coloring the vertices in our GNs. So I not only have a radius, but I have a finite set of colors with which I'm coloring the vertices. And when I'm sampling and I look at the distribution of things I obtain, I also record whatever colors I see on the various vertices in my neighborhood. And this carries more information than the previous one. The question is, does it really, or are these two things actually equivalent, that I can regain all information from the non-colored version? Well, it turns out that you cannot. There's a very major difference that can be seen very easily if you just look at this previous convergence, this localized convergence. If you have a sequence of graphs, and then you take a different sequence of graphs where every single graph in this new sequence is 2 disjoint copies of the original sequence. Then if you take these completely localized samples, you won't see any difference between the two. Right? However, if you're doing colored things, then in the second sequence, you can color one disjoint copy in one color and the other disjoint copy in a different color. And then you will see samples that are completely monochromatic. Okay, so however you do your local samples, in the 2 disjoint copies case, you will only see monochromatic samples, whereas in the original sequence, you will see a mixture of colors if you're working within the same graph. And another difference, I don't necessarily want to go into all the details, but if you're doing deregular graphs, meaning every vertex has degree exactly d, and you grow your number of vertices and you can generate these in a random way, there are 2 different models. Either you generate random bipartite deregular graphs, or you generate just random deregular graphs. In the first case, when you have these bipartite things, you always have a coloring where you color one class red, the other class blue, and that will again give you samples where you will see half size monochromatic subsets. So half size monochromatic empty subsets and that's not going to be the case in the non-bipartite case. Okay, some probabilistic things that go into the non-bipartite case not being exactly like that. And this is called the local global limit. So you do localized samples, but somehow the coloring allows you to extract more global information about the graph sequence. Say you're not having 2 disjoint copies. And the limit here, the limit object, is what's called a graphing, proved that these are the local global limits by Hatami, Lovas, and Segedi in 2012. So what exactly is this graphing? So this is a weird object, perhaps. It's a graph G over a probability space. So the underlying set is omega, on which you have the sigma algebra B and the probability measure lambda. And you have this integral relationship between integrals of degrees taken over certain sets. Now, what this tells you in a formula is that if you take 2 measurable sets of vertices, A and B, then there's, among other things, 2 ways of counting edges going between A and B. One, you look at vertices in A, you look at their degrees, and you integrate that. So degrees, I mean, going to the set B. And then you can do that from the other side, from B. And you have to force this equality to have this double counting giving the same result. Okay, so it's not automatic that this thing happens. Okay, so this is the definition of a graphing. Note that you will have the graph actually having a vertex set on a probability space. So the limits here are not going to be graphs on a countable set of vertices. And even in dense case, that's not going to be the case. And there's a very simple reason for why that cannot be the case. And that's because we define everything through samples. And if we want to do samples and sample uniformly at random, we'd like to extend this sampling to the limit object. And if you have a countable set of vertices, you cannot possibly sample uniformly from this countable set. And that's why we're taking some probability space here. Typically, one will be looking at a vertex set being the interval 0, 1, but in other cases, it's more convenient to work with more general probability spaces. So in all of these cases, these limit objects will form a compact metric space where the metric is whatever the convergence induces. And a natural question is, well, we define these limit objects, but is this the true space of limit objects? So are simple finite graphs dense in that compact metric space that we've defined? And in the dense case, so for the graphons, the answer is yes. So any graphon, we'll see exactly what a graphon is soon. Then the answer is yes. For graphings, if you look at the Benjamin-Ishram limit, so this local uncolored limit, then this is unknown. And for a very strong group theory reason, so there are strong connections there to group theory. It's been an open question for a long time. However, if you look at graphings in the local global convergence, then it's been answered to the negative by Kuhn and Tom in 2019 that it is not the case that simple finite graphs are dense. So graphings are a relatively nice space of objects, but they are not the true limit space of finite simple graphs under the local global limit. And it is not really known what the true closure of finite simple graphs are or is. So let's get back to dense sequences. And we see that graphons are the closure of finite graphs under this sampling metric. So we have a compact metric space. And what's very nice about compact metric spaces is that if you take any other metric on this space that on one hand is comparable to the original metric, so the topologies have inclusion in one direction, and you know that this other metric also gives a compact space, then these two topologies are actually the same. So the two metrics are going to be equivalent metrics. So in this dense setting, this actually leads to a whole host of equivalent convergence notions for dense graph sequences. One of these notions is the so-called cut metric. I'll not go into details about that. Homomorphism density convergence, also known as left convergence. We'll see about this in more detail and why it's called left convergence, and right convergence as well. And as I said, we'll be talking a bit more about this homomorphism density convergence because it's the thing that relates the most directly to sampling convergence. So what exactly are these densities I'm talking about? So we look now at some small graph f on k vertices. And this is going to mimic our sampling rather closely, but it's not going to be exactly the same thing. So we take some f on k vertices and look at the map from the vertex set of f onto the vertex set of g. You could think of this as sampling k vertices within VG. However, we are not going to look at the span of those vertices in VG, but instead something slightly different. So we'll be looking at this following product here. So what's happening is that for every single edge in F, I will be checking whether its two endpoints are mapped to vertices in G who are connected by an edge. If they are connected by an edge, I see a value 1, otherwise I see a value of 0. And so this product actually tells me whether this map phi induces a graph homomorphism. So whether it's an edge-preserving map from the vertex set of F to the vertex set of G. So this is 1 if it's a homomorphism from F to G and 0 otherwise. And then we can define the so-called density of a graph, small graph F in the big graph G. At least that's the way we like to think of it, that F is somehow the sample we try to find in the big one, as taking this product, summing up for all possible maps from the vertex set of F to the vertex set of G. So I'm looking at all possible samples I could take, and then I'm averaging out. This can be reformulated as the probability of a random vertex map phi being edge preserving. And how this relates to our sampling notion defined earlier, our sampling notion looks at spanned subgraphs. And using the sieve method, you can go back and forth between this notion and our original sampling notion. Okay, so if you define convergence with our original sampling notion, then that's going to be equivalent to whatever is happening here. So I'll define a sequence being left convergent if this sequence is convergent for every single simple graph F. And left convergence because I fix this test graph F on the left-hand side of this TFGN. And you've seen, maybe you remember still on an earlier slide, there was a notion of right convergence. That's essentially when you swap F and GN here. So let's look at the limit theory, where I would like to show you how exactly the limit objects look like. So I've been talking about graphons, and I've still not told you what exactly these graphons are. So let's try to find out what a graphon should be, what a limit object would be appropriate for this convergence notion. So if we want to have a limit object and we have some convergence defined through these densities, then it would be natural to wish for two things to happen. First of all, we're looking at limits of graphs. So the limit should be something that looks like a graph. Okay, so it should have some graph-like features. The second, since we define the convergence through values of these densities, it would be nice if the limit object had a natural notion of densities itself. So we don't just have an abstract limit object whose density is defined as the limit of densities of a sequence that converges to it. Okay, so we want a natural way of figuring out what the density of a graph F is in this limit object without having to go through a sequence that converges to the limit object. Okay, and so what would correspond to these densities TF dot if this dot is one of these limit objects? So let's look at the formula. So this TFGN is an average of these products where the number of terms is typically tending to infinity. So if the number of vertices in Gn tends to infinity, then I'll have an average where the number of terms tends to infinity. Now this is an average, so the natural limit, at least to me as an analyst, the limit should be an integral. Okay, so the limit of averages where the number of terms tends to infinity should look somewhat like an integral in an appropriate sense. And how exactly that? So we'll have an integral and we'll have the same type of product over all edges in F. And it turns out that instead of that characteristic function that tells us whether an edge is mapped onto an edge, we'll be forced to have something slightly more general, some function W in two variables. The part of two variables is logical. We have two vertices that are mapped, and we checked originally whether they are connected or not. So that was two variable as well. We should preserve that in the limit. The integral should be over all vertices in F, because that's what we took the average over as well. And it should be integrated over a set of volume 1. And in all coordinates, it should have the same size. So we can reasonably assume that it is of the form 0, 1 to the power number of vertices in F. Okay, so this is average-like and looks very much like a reasonable limit to those average sums that we were looking at. And this is what we will define as the density of F in this limit object W. And now let's figure out what this W should actually be as an object. So it's going to be a function, two variable one, as we said, with its values taken from 0, 1 squared. So its domain being 0, 1 squared, and it's going to map to the closed interval 0, 1. So it's not going to be 0, 1 valued like the characteristic functions in the finite graph case. And we'll get back to why exactly that is happening here. And the other feature is that it should be symmetric in its two variables. Okay, whether we look at an edge with vertex 1 and vertex 2 or the other way around, that shouldn't play a role. So this W, which is a symmetric measurable function from 0, 1 squared to 0, 1, you can also think of it as a generalization of the adjacency matrix of a graph. Right? You just rescale this adjacency matrix into as a function on the unit square by putting 0 and 1 wherever appropriate, and then this function is a generalization of that. It's not going to be a step function, but something that's measurable. And so the limit object is going to be a graph with vertex set 0, 1. And as I mentioned, this is a generalization of the adjacency matrix. So this WXY is going to give the weight of the edge between a vertex X and a vertex Y. And what's important to note here, as I mentioned, is that it's truly a weight. So there are going to be numerous examples where the limit cannot be just 0, 1 valued. You have to allow weights that are strictly between 0 and 1 if you want to cover all possible convergent graph sequences. And another way of formulating this, since we're talking about samples and a probabilistic approach to all of this, that this weight can also be interpreted as the probability of seeing an edge between X and Y. So you could think of W as being a random graph and X and Y being connected with probability W, X, Y. And a theorem by Lovász and Szegedy from 2006 says that if you're given any convergent sequence Gn of graphs, so left convergent, then there exists a corresponding W, which is measurable and symmetric, which represents this limit for any graph F, and this is what we call a graphon. So a graphon is a measurable symmetric function W from the unit square to 0, 1. And the interesting part is that this closure of finite graphs under this metric being the space of all graphons is this statement here: to any such symmetric measurable function, there exists a sequence of simple graphs that converge to it. Okay, and this is what's not true in the sparse case, and why we have trouble there is because even though we have this graphing as a limit object, we are having, so the problem is that it's not possible to, using a graphing, take finite samples and have those converge to the limit object. So here, the idea of the one possible proof of this is to say you start with this W, which is a graph with an infinite vertex set, and you sample k vertices at random, and you look at whatever finite graph that gives you. This gives you a random sequence, a sequence of random graphs. So if you increase k to infinity, you have a sequence of random graphs, and with probability 1, that is going to converge to W. That's the idea behind that. And for some reason, that for graphings is not going to work. And that's a very stark contrast between these two theories. Now, what I've not touched upon is uniqueness. So not only do you want this space of limit objects to be the closure of whatever you're looking at, but you're also interested in how unique is the representation of the limit. So can it be that two different W's actually represent the same limit? And the answer is very much so, yes, but only to the degree that is natural. What do I mean by that? So even for finite graphs, if you take a graph with labeled vertices and you relabel it in a different way, then those two graphs are still essentially the same graph. They are isomorphic. So renaming the vertices is not going to change the graph as a structure. And that's the same thing here. So for such a function W, the vertex set is the unit interval. Now, if you relabel that unit interval in a different way, then it's still going to be representing the same thing. So what relabeling in this case is going to correspond to is having some measure preserving transformation phi on the underlying set. So essentially a permutation. It's not necessarily a bijection, so there are more technicalities to it, but you may think of it as a permutation of the underlying vertex set. And that's it. So there are no hidden other reasons why two graphons would represent the same limit other than there being some appropriate transformations that bring one to the other, with some added technical caveats there, but that's the essence of it. So these graphons, so this space of functions that are symmetric on the unit square and take values between 0 and 1, they actually form a pseudometric space. So you have to factor out these equivalence classes that come from these permutations. But that's the true metric space after factoring out, and that thing is going to be compact. So to finish off, let's try and figure out how this can be generalized. So the dense setting, and I've called this beyond boundedness. And why boundedness? Well, if we take these graphons, these are functions on the unit squared that map into the interval 0, 1. Such functions can be used to generate a vector space of all bounded symmetric functions on the unit square. Okay, that gives you a nice vector space structure, but the metric that we've talked about also extends to this, but it's still a pseudometric. So you're not fortunate enough to have, say, a normed space that you can work on. You only have a metric space if you factor things out. So unfortunately, no normed space structure here, but still. So as I said, these are bounded functions here. And that comes from the fact that when you're looking at sequences of simple graphs, then there are no multiple edges. And edge multiplicities are the things that could lead into the unbounded setting. So the questions that can be asked here is, what larger space can these densities apply to? Can I extend this space of functions to something larger in which still that integral formula makes sense and gives me a finite result? Also, if I go beyond this space of graphons that we've been looking at until now, we will eventually lose compactness of the space. And I mentioned that compactness was key to various convergence notions being equivalent for graphons. So a natural question there is, what happens to these different notions? Do they still remain equivalent? Are some implying others, or do they essentially become completely independent notions of convergence that luckily on graphons coincide, but otherwise there's no implication between them in any direction? And one direction that was looked at by Borst, Chase, Kohn, and Zhou was in the direction of, well, instead of looking at L infinity symmetric functions, you look at LP versions. So not bounded anymore, but still in some LP space. And that allows you to look at densities of graphs where the maximum degree is, let me get this right, less than P. So if your maximum degree in F is less than P, then some generalized Hölder inequality allows you to state that these densities are still finite reals. So you can still do some sort of density within these things, but only for some subclass of graphs. Something really abstract, and it's been done by Lovas, Segan, and myself, is instead of looking at graphons taking values that are real numbers, we'll allow them to take values in a vector space, actually a Banach space. Now, this seems very abstract and perhaps completely unreasonable to look at, but it turns out that if you look at sequences of multigraphs instead of sequences of simple graphs, then at a certain point, you're forced into a formalism that is best captured by looking at such abstract objects. Okay, don't want to go into details here. And another direction that you can go into is, well, if you push this LP-ness even further, so going from bounded functions to LP functions already allows you to have some type of singularity in your function. If you push this even further, you would arrive at measures on the unit square instead of a function. Now, if this measure is absolutely continuous with respect to the underlying product-Lebesgue measure, then taking the Rodon-Nikodym derivative would correspond to some L1 function. Okay, but it's actually possible to push this beyond that. Now, in this case, it's a huge question mark what you can say about these densities. How can you even define the density of a graph in a measure that's so singular that you can't really wrap your head around that integral? And the next talk is, as far as I know, partly going to talk about this. If you are looking at measures or very singular things on the unit square, when and how can you define densities there? That was all from me. Thank you very much.
Tiling, and these Penrose tilings are known to become more and more similar. If you take any one of them, there is an uncountable number of such tilings, continually many such tilings, and the property is but if you look at any particular finite piece of a tiling, you will find this in every other tiling, except it's continued in a different way. And in fact, you can define how dense this particular, so say this star pentagon will occur in every tiling infinitely often. So these Penrose tilings are examples that show that you can have this property of becoming more and more similar in a highly non-trivial way. Now, so again, we are back to this question. But besides, so what does it mean, a template? Well, it's related in a sense to convergence, so that actually more and more similar should be translated in an exact mathematical notion of convergence. And the template is really closely related to having a limit object. So it's a single object to which these graphs become more and more similar. So that would be a template. And the previous talk, we have seen that for dense graph sequences, there is a notion of left convergence, which is essentially equivalent to sampling. David mentioned that there is a right convergence that is actually related to all sorts of models in statistical physics. But I will not go into this. And there are limit objects called graphons. And in the bounded degree graph sequences, there is left convergence, again, coming from a different sampling. That was the name of non-localized sampling. And that was the localized sampling. Right convergence, again, various statistical physics models will converge, and collectively they define right convergence in one way or the other. And again, limit objects, graphings were introduced. And one of the goals of this talk is to come back to what happens in between, and we'll talk about Markup spaces and double measure spaces. But I think let's recall some more facts about dense graphs. So David mentioned that you can define the distance of two graphs. In fact, there are various notions of distance between two graphs. One comes from sampling, but there are the more structural, more global notions of distance, which I don't have time to go into. And then the convergence is equivalent to the Cauchy property and in this distance. And the graphons will form a metric space, and it's very important. This is a compact metric space. I'll show you at least one application or maybe more where this really plays a very important role. Now, these are some additional things which I will not talk about, but I would like to mention. There are these famous regularity partitions or semi-ready partitions. They can be defined for graphons. And this is closely related to an algorithmic theory here for large graphs and graphons. Spectra, whoever is of a little bit algebraic being, they will be happy to learn that spectra of graphons are very nice, and they are the limits of spectra of graph sequences which tend to them. And this is also an important property. And there is an extremograph theory applications which often go through extremograph theory. Actually, to this I will come back. So let me start with showing you some applications of graph limit theory. In fact, in the dense case. And so I will talk about the existence of optima, some very strange results about finite forcing, about the local extremograph theory, and an application in probability theory. So this is really just the motivation of much, which I will talk about in the sequel. So let's look at the first year calculus exercise. Let's minimize x cubed minus 6x over non-negative x's. You have probably already computed that this happens at square root of 2. That, minimum is attained at square root of 2. It's down here. So one thing is that the minimum is not attained in rational numbers. And that means that it's very useful to have real numbers. Just imagine that you don't like real numbers, like say ancient Greeks didn't like them. Then you have to express everything in rationals, and that becomes terribly awkward. You cannot talk about a single number like square root of 2, but you have to talk about maybe arbitrary close approximations and sequences that tend to they tend to nowhere because of square root of 2 doesn't take. So introducing real numbers is very useful. Now let's look at a graph theoretic problem. And that's a valid problem in graph theory. Find the minimum density of 4 cycles. This density, this is the TC4G that was introduced in the previous talk. So the minimum density of 4 cycles in a graph which has edge density half. So half of the possible edges is present. Now there is a old theorem actually going back to the 50s by Erdős. In one of his papers, he used this argument that this density is actually always larger than 1/16, but it can get arbitrarily close to this. For example, if you take a very large graph at random, then the edge density will be 1/2 and the 4 cycle density will be asymptotically 1/16, but a little bit larger. But if n tends to infinity, it will be about 1/16, 10 to 1/16. So again, it is an optimization problem. The minimum is not attained among graphs, because it's always strictly larger than 1/16. So graph limits are useful. In fact, we know that the minimum must be attained for some graphon, because the space of the graphons is compact and it's easy, more or less by the definition. Such a density is a continuous function on this space, so it attains its minimum. In a minute, I will come to what this minimum is. Actually, yeah. In fact, it's the constant 1/2 graphon. And actually, the proof gives a little more. It's not hard to prove. And the proof gives a little more is that this is the unique minimizer. So that's the only graphon on which it is attained. And this way I come to finite forcing. Coming back here. So what does this say? It says that if I tell you that here is a graphon and the edge density is 1/2 and the 4 cycle density is 1/16, then you know it is this single graphon. So it's uniquely determined by just telling you these 2 densities. So this means it's finitely forcible. And in general, this notion of finitely forcible means that there is some finite list of graphs and some finite list of densities, so that these conditions, if U is a graphon, then they determine U uniquely. Of course, unique here means, David talked about this, but unique means that there is you can always sort of reshuffle the unit interval. You can turn it around, cut into 2 and exchange, do any kind of measure preserving transformation on it. But that's all. Up to that, except for that, this U is determined unique. Well, here was some idea. So if you have a finitely forcible graphon, then you can always, take the difference and square and minimize. So you can always formulate a solution of such a system of equations as a minimization problem where the minimum is 0, just the sum of squares of differences. So it's an optimization problem on graphons. What is that? You write up it's a quadratic function. It's easy of these densities. It's easy to turn it into a linear function of densities. And you want to minimize this linear function of densities. And actually, this is an absolutely generic problem in extremal graph theory. In extremal graph theory, we are always talking about questions like, if the edge density is 1/3, what is the minimum of the triangle density or the maximum, and so on. And so these finitely forcible graphones are sort of templates for optimal graphs, optimizers in extremograph theory. And so if we understand the structure of them, then we get important information about extremograph theory. So let's look at some finitely forcible things. The constant functions are finitely forcible. That was essentially for the constant 1/2. I already told you this for every other constant. It's the same thing. And that's actually in finite graphs, it translates to a very nice work by Chung, Graham, and Wilson on quasi-random graphs. Because again, if you use the limit space, you get very simple formulation of this fact. Namely that this is forced by those two conditions. If you want to stay within finite graphs, of course, in 1986, they had no other choice than stay within finite graphs, then you have to talk. It's a rather complicated notion that you have to introduce, but it's a very nice and important paper. Now, this was already in the graphone age with Vera Schorsch. We proved that every step function. By step function, I mean something like that. You cut up the unit square into rectangles, and there is this grayscale indicates the value of the W function. So it's a function on the unit square with values between 0 and 1, and that's a grayscale presentation of that. And for a while, we were quite sure that these are all, that there could be a very nice, because all the known examples in extremograph theory fit into this. But then with Balázs Szegedy, we found a couple of more examples, actually, not a couple, many more examples. I'm just showing you here a couple of them. So you see that they are beginning to become complicated. So what can you say about finite forcing? So here is more or less the only thing that you can say in a positive way about finitely forcible. You have all these graphones, they form a compact space. Now within this compact space, finitely forcible graphones form a bare one category set, a meager set, I think that's sometimes called. And the rest forms a bare two category. So there are many more non-finitely forcible functions than finitely forcible functions. At least there are not finitely forcible functions. But in fact, you can actually explicitly, like x plus y over 2 is not finitely forcible. It's not so trivial to prove, but this is not finitely forcible, or x times y. Actually, any polynomial in x and y with values between 0 and 1 is never finitely forcible, except for the constant, which we saw. And now, to round up this application, so we had this idea that finitely forcible is the template, and therefore we should understand how finitely forcible functions look like. And with Balázs Szegedy, we formulated several conjectures, and we were sure that they were true, and if they were true, then they would be very helpful in extremograph theory. However, in the last, 7 or 8 years, Kral, and these are many of his students and collaborators and postdocs, young people, they disproved all of those conjectures. And that would be like sort of bad news. But what's interesting is that by disproving them, they proved something very interesting in a different direction. So let me try to formulate just one of their results. This is a graphone. You think it's a cat, but actually it's a graphone. And now what they prove is that you can embed this into a graphon, I mean, shrink it by a factor of 2 and then put, these are here, these things here are appropriate functions. So you define the extension of this function here appropriately so that this becomes finitely forcible. And so this means that there is a huge variety of finitely forcible. Anything, any graphon here can be extended to a finitely forcible graphon. And this is not only finitely forcible, but they give a very explicit set of, I don't know how many, let's say 200 graphs, so that the densities of these graphs determine this. And this set is universal. It doesn't depend on what graphon you want to embed this. So it's a very surprising thing. So it says that every such graphon is encoded into that 100 real numbers, which tells you the densities of these graphs. Now 100 may be in fact 500,000, the finite set. And this is an encoding which is basically somehow formally very simple, because it just involves the density functions, this TFG function, TFW function, some explicit integrals that determine it. So this is something very exciting grew out of disproving some conjectures. Now let me talk a little bit about local extremal graph theory. Let's go back to beginnings of early days of graph theory in 1959. Goodman proved the simple inequality, the density of triangles in a graph G, plus you add up the density of triangles in its complement, you get, this is the minimum, and it's about 1/4, which is about the density of the triangle is about twice the density of a triangle in a random graph with density 1/2. So random graphs with density f/2 are minimizers, at least in an asymptotic sense, of this sum. In terms of graphons, it of course becomes much neater to state. It says that the density of the triangle in a graphon plus the complement, which is 1 minus this graphon, subtracted from 1, is at least 1/4. It's a clean inequality. And this is equal to the density twice, the density of case 3 in the 1/2 graphon. So this is an exact statement that the identically 1/2 graphon is a minimizer for the left-hand side. Now, Erdős raised the problem that maybe this is also a property of other complete graphs, and in particular K4. He conjectured that this is true for K4, but that turned out to be false. And much later, Thomasson gave a counterexample. Now that says that there are graphs for which this analogous natural generalization is true, and there are other graphs for which it's not. And so people began to call a graph common if this inequality is true for every W. So in other words, the minimizer is the identically 1/2 function. That some graphs are common, some graphs are not common. There are bipartite graphs are probably all common, but among non-bipartite graphs, there are common graphs and there are non-common graphs. And this is not so easy to tell about a particular graph whether it's common or not. Not a very good name, because it's more common to be non-common. But anyway, was defined long ago. Now, the graphons suggests that there is an approach here which is sort of a local extremograph theory. So you look at this inequality, but you only want the R1/2 function to be a local optimizer. What does it mean? Local, it means that for every W which is close to this identically 1/2 graph 1, for example, in the supremum norm, this should hold. Now, strangely enough, this was already implicitly proved by Fronek and Rödl that K4 is locally common in 1992 without using the language of graph 1s. And accordingly, it's a rather awkwardly formulated theorem because you somehow have to prove that if you take a random graph, a large enough random graph, and perturb it a little bit, then the corresponding inequality will be still true, but there will be two error terms, and you have to somehow say that one error term dominates the other. So it's an awkward thing. But here, this definition is, of course, nicer. I'm advertising graph 1s here, of course. But this was a very interesting paper. Now let me just sum up and state an interesting result by combining the work of several people. Every graph that contains K4 is locally common. It's always locally common, but never common. So somehow the local version is contradictory to the other one. This, on the other hand, this sort of saves or salvages Erdős's original conjecture in the sense that at least it's locally common. So, of course, there are other extremal problems in graph theory for which you can ask the local version. Not too many are worked out, but it's definitely a very meaningful question, in particular in this setting. Now, finally, this is somewhat more technical. Sorry? 30. Oh, there, okay. So large deviation theory for random graphs. So here is a question that I think many people have asked. So suppose I take this GNP is a standard Erdős-Rényi random graph. You have n points, and for every pair of points you flip a coin, and with probability P you keep the edge, and with probability 1 minus P you don't put in an edge. And but now you don't take this graph, but you also condition on the triangle density to be larger, to be at least T. Now, the expectation of the triangle density is P cubed. So, so this means that you go above the expectation by a constant. This is called large deviation theory in probability theory, and Varadan is the famous probabilist who worked out the theory of these large deviations. However, the trouble was for a while that his theory doesn't apply here because it's on a continuous space, continuous valued random variables, and so he needs a compact space to work in. But of course, if you extend the problem to graphons, then you will have a compact space. Now, I won't go into details because they become highly technical. First, as a threat or a threatening thing, this is what it leads to. This is an entropy function, and you want to maximize this integral of the entropy function subject to these kind of these are integrals themselves, these constraints. So constraints on various integrals involving this function W. So this is a usual variation calculus problem. And actually it can be solved. I just want to mention one consequence of it, which is sort of, it's not so easy, but it's reasonably natural. So if this T is larger than P cubed, so T is the lower bound on the triangle density, and the P is the edge density, so it's larger than, but not much larger. Then if you take an Erdős-Rényi random graph with edge probability P, but you condition it on being the triangle density being larger than T, then this becomes a random Erdős-Rényi random graph with the edge probability T to the 1/3, with errors which I have not included. So this was worked out by Chatterjee and Paradan. And then this, a lot of other large deviation theory could be extended to this. Okay, now I come back to this topic that David already announced. And this is a current focus of our research. This is where the densities are somehow intermediate. So one is LP convergence. He mentioned this, and I will not go into it. Bolk, Chase, Cohn, and Zhao worked out. This is the LP graphon is basically a function W, which is LP, which is in LP. So the original definition is a bounded function. So this is a generalization. And if you compute the edge density for P, if it's really not bounded, then the edge density will be actually little n, so 10 to 0. So this is indeed a kind of intermediate density. I will not describe this in detail. And then there were several attempts in some kind of convergence. I call it scaled convergence by Peter Frankel. And the limit objects, he calls a graphoning. And there are two other notions of convergence, shape convergence and action convergence. Balázs Szegedi was involved in developing both of them, and they have appropriate limit objects called S-graphon and graphon. Now, this looks like discouraging because there are different notions and different limit objects, but actually on closer inspection, it turns out that S-graphons and graphops are equivalent. Graphop is a functional analysis approach, and this is a more probabilistic approach or measure theoretic approach, but they are actually equivalent objects. And the LP graphon is a special case of this. And graphoning is also essentially these with some bells and whistles, which I will not go into this. So anyway, what are these limit objects? So if you look at all of them, including the old ones, graphings and graphons, you can see that there's a very simple thing, but that's crucial. You have a notion of a random node. So there is a uniform distribution on the set of nodes. And it's fairly natural to also assume that you have a notion of a random edge. So you have a uniform distribution on the set of edges. In a finite graph, this is trivial. But if you want to guess what the infinite version of this is, well, a random node is, say, the 0-1 interval, as it's in the case of graphings and graphons. I mean, that generalizes. And a random edge corresponds to a symmetric probability measure on this unit square. Because a point of this unit square is like an edge. It's a directed edge, but if you make it symmetric, then it becomes undirected. And so you have a probability measure on the unit square. I will forget about random node for the rest of this talk, which means that instead of the 0-1 interval here, I can take just any sigma algebra, and I will take a Borel sigma algebra there. So, and this leads me to Markup spaces. So a Markup space is a Markup space. First of all, you have a Borel sigma algebra. If you are not familiar with this, it just means you look at the Borel subsets of the 0-1 interval, they form a sigma algebra. And the Borel sigma algebra is everything which is isomorphic to this as a sigma algebra. But almost everything you ever think of, at least every countably generated sigma algebra you ever think of will be like this. So for example, all the Borel subsets of a unit sphere, or actually Borel subsets of any Borel set, they will all be isomorphic. So this is fine to assume. And eta is a probability measure on the square of this, so a sigma algebra. So you take J times J and or whatever the products of Cartesian products of measurable sets generate. And the only assumption is about, well, equal marginals. Let's make it simpler. Let's assume that this eta is symmetric. If you interchange the two coordinates, you get back the same thing. If you don't assume that this is really a surprising and not quite trivial fact, that this is equivalent to a Markov chain with a stationary distribution. And if you assume symmetric, then it's equivalent to a time reversible Markov chain with a stationary distribution. So this is very heavily into core probability theory. Now, so these Markov spaces are supposed to serve as limit objects, and in the previous examples, it turns out they are really maybe sometimes equipped with an additional measure on the points. They are the limit objects. Now the question is, are these rich enough? So how much of graph theory extends to these Markov spaces? They look like a very weak structure, just a Cartesian product of the most standard sigma algebra with itself, and any measure on it subject to the condition that it's symmetric. So that looks like a very, very poor object. So how much graph theory can be extended to these Markov spaces? And then, of course, which graph sequences have limits as Markov spaces? There are some examples which I mentioned, which I didn't describe the sense in which they tend to these Markov spaces, because they are somewhat difficult to describe, and I don't have the time, but they can be defined in a very reasonable way. And of course, then is the reverse question: which Markov spaces are limits of graph sequences? It depends on what sense. So graphons are special Markov spaces where the eta is absolutely continuous with respect to pi times pi. So respect to the product measure on the unit on the square, and this is and in this case the Radon-Nikodym derivative of eta with respect to pi cross pi is the graphon. So which Markov spaces are limits? Those graphons are limits. With graphings we saw there are problems. So This is all these questions are unsolved, but we work on it. So let me report some facts that we can do. So first of all, one thing is that one important branch of graph theory is flow theory. Let me show you that flow theory has a very nice extension to this setting, to this measure theoretic setting. So let's look at a graph. Now, a flow or a circulation means that you assign a number, general real number, to every edge. Now, you do this in an anti-symmetric way. So you take a reference orientation of the edges, and if you reverse an edge, then you negate the corresponding flow value. It's natural, that's the way to do it. And the condition is that the inflow into a point is equal to the outflow from that. We call this the flow condition. Now, how do we translate to the infinite setting these flow values? The first approach is that it's a function on the pairs. But there is another way of looking at it. It's also a measure on the pairs. Because if you take on the set of edges, if you take any subset of the edges, then you add up the values, and that gives you the value of the measure. Right? So it's a finite measure on the subsets of the edges. And it turns out that the second view is better to generalize, or has a more natural generalization. Both approaches have been studied, but I would like to show you how simple this becomes. So what is a circulation? I forgot to say it, that the circulation is such an assignment which satisfies the flow condition at every point. This generalizes to a measure on the unit square, or the square of the underlying Borel space, with equal marginals. Why are they equal? Well, what is the marginal? If I view this as a measure on the set of edges, on this pair, so what is the marginal? The marginal will be, one marginal will be the outflow, and the other marginal will be the inflow. So these have equal marginals. Now, just to translate one of the results from finite graph theory, there's the Huffman circulation theorem, which gives you a necessary and sufficient condition for the existence of a circulation where on each edge there is a lower bound and an upper bound on the flow value. This generalizes to the Markup space, or this measure theoretic setting, as follows. We have two measures on 0, 1 squared. One is supposed to be the lower bound and the upper bound. And we want to find a circulation which is between them on every set. So this inequality means that on every measurable set, this inequality should hold. And then the condition is that, well, there's a trivial one. The lower bound should be less than or equal to the upper bound. And there is a not quite trivial one, which says that if you look at the set of edges going from X to its complement, and you take the lower bound on that, that should be less than or equal to the upper bound on the reverse set. So this set of edges in graph terms is a cut. We call it a cut in graph theory. The set of all edges that go from one side from one set to its complement. And and that's the Huffman circulation theorem, this finite version, that if you take any cut, then the lower bounds summed over all edges in this cut, which is the measure of this cut, is less than or equal to the upper bound on the reverse cut. Or here is you can generalize the famous Maxwell cut theorem. You can define a flow from S to T. In the finite case, again, this is a measure on the set of edges. And the value of the flow is the violation of the flow condition at S, and it's a negative on the violation at the other end. Now, if you want to generalize this to measures, it turns out that the flow of value, say 1, just fix it as 1, is a measure on the square such that the marginal difference of the marginals is the difference of these two Dirac measures or point measures, measures concentrated on S, on T minus measure concentrated on S. And then the Maxwell mean-cut theorem, I don't formulate it. You can now guess what it means. It's just, again, a cut condition, but now only cut separating S and T. And then it turns out there is a lot of other good, nice results in flow theory, decomposition of flows into paths, integral potentials under certain conditions, multi-commodity flows, and they generalize nicely to this measure theoretic setting. So at least one branch of graph theory, flow theory, is generalizes. Now, finally, I would like to come back to the issue of sampling, which was the main introductory point of view by David. So how do you sample from a Markov space? Now, this is a difficult question, and we have some unpublished results on it, but there is one published result, and I would like to focus on that. So this is a special case, but it's a very nice special case. The special case of is the following. You take the unit sphere. Now, first we start with defining a graph on it. It's of course infinite graph where you connect 2 points if they correspond to orthogonal vectors. So the North Pole is connected to the equator, every point on the equator. That's the neighborhood of the North Pole. I denote it by H3, this graph. Now, this graph defines a Markov space because if you look at all edges on the set of, you need a measure on the set of edges, but all edges are alike. So this measure on the set of edges is a you can define a uniform measure on the set of all edges. If you want to be very fancy, you can refer to the HUN measure with respect to the rotation group of the sphere. So that's easy. So there is a uniform measure on all pairs. Now, however, you would like to define a measure on homomorphisms from a graph, from some graph, say the Peterson graph or something like that. And if you have a measure on homomorphisms, then you have a notion of a random copy, more or less. We'll see that's a little bit not so easy. And the density of homomorphisms has to be defined. And that will be something like the total measure of copies of this. So it all depends on the normalization, of course, but in a finite case, if you count the triangles and you normalize it by n cubes, then you get the triangle density. And so the density of the homomorphism density is like the total measure. Now let's look at some simple examples. So for example, if you look at the triangle, we see then a random copy is trivial because again, all triangles are alike. So you have a hard measure on the triangles or a measure on the triangles. You can simply average a measure on triangles. But it's non-trivial to define a density. So we have a finite random copy, then the total density is 1, but that doesn't say anything. If you do this for a graph, then that doesn't tell you anything about the triangle density. Here is the most interesting example with C4. So suppose you want to define a random copy of C4. So you can start picking one point and mapping it somewhere. Say you map it on the North Pole. I mean, all points are alike. Say you map it on the North Pole. Now this has two neighbors in C4, which are now 2 points on the equator, say random points, independent random points on the equator would be a natural choice. But if you choose any 2 points on the equator and you want to find the image of the fourth point, then the fourth image of the fourth point is either the North Pole or the South Pole. There's no other possibility, which means that in this map, one pair of opposite vertices will be mapped onto parallel vectors, the parallel or anti-parallel, and the other pair is mapped anywhere on the equator, so there is no restriction on their distance. So now you can interchange the role of the two pairs, and that means that there is no natural notion of a random force cycle in this graph. So there is trouble. It turns out that with C5, there is no trouble, but it's non-trivial how to define a random copy of C5 in this graph. So here is one approach. You can take an ordering of the vertices of the graph, and you can map. I mean, I did already this for C4. You can map one by one the points. Now, as long as the degrees are at most 2, then you can choose them one by one. Maybe with 4 cycle we run into trouble, but you can still choose them one by one. We mapped the 4 cycle into it. It just was not uniquely determined, the distribution. So you get a probability distribution on this, and that depends on the ordering, as we have seen for the 4 cycles, on which order you map the points. However, with the only exception of the 4 cycle, you can multiply this density function by an appropriate density function. So you have now a probability distribution. You can figure out a density function so that if you multiply this distribution by this density function, then it will become independent of the ordering in which you started. And that gives you a notion of a random copy, which is independent of in which way it was constructed. Now, so let me just finish with an example. So this is the notion of the density of F in G. But for these cases, when it's not a graphon, it's a more singular measure on the square, you have to redefine the rescale or renormalize it. And it turns out that a good normalization is that you take this density and you normalize by, you take the edge density in the graph and you normalize by an appropriate power of it. The number of edges is in the exponent. If you do that, then you get something like that. And then if you take some natural sequence of graphs which tends to this infinite graph, and that's very tricky how to define it, but there is such a thing, then these values will tend to some values in the limit. And I just, for the fun, I give you 3 specific values. For every 3, this T star value is 1. That's actually true for every graph. So if F is at 3, then for every graph, this T star value is 1. If you have a K3, the triangle, then the value is 2 over pi. For C4, the value is infinite. For C5, some complicated number, which is more difficult to compute. Okay, so maybe before reading this out, I would like to say that this fact that we are relating now to more and more measure theory analysis is actually the whole point in developing this whole theory. We would like to pull in as much of the big toolbox of classical mathematics as we can. And that's why I wanted to show you that measure theory can be pulled in, geometry can be pulled in, like in the last example, and functional analysis comes in, and a number of other things, other areas of mathematics come in, which we haven't touched here. So thank you very much.
Is there any question?
Thank you for bearing with us so long in this late in the day.